Hi there guys, so this is 15G. This is a really nice little bit of maths that's turning up here. This is the Chinese postman problem, and quite amazingly this first problem was posed by the Chinese mathematician Quan Mei Kuo in 1962. So this is really recent mathematics, but in a sense it's just like puzzles. Okay, so I think it's worth you just reflecting briefly for a couple of minutes on those opening puzzles from the chapter where we talked about the Königsberg Bridge problem. So I've just tried to draw this one out here. Here we go. We've got the river in the middle. We've got some islands. Got an island here, and if this isn't an island, it's at least a bit of land in the center of the river, and you've got two edges, of course. Spending a lot of time coloring in here. Okay, and you've got the problem where you need to traverse all of these bridges, and as a tourist potentially you're going to start in the train station. I don't know where the train station is in Königsberg or Kaliningrad in Russia as it's now called. So you have to traverse all of the bridges and try not to cross them more than once. Okay, and you could potentially start in one place and end in another place, but ideally you start in one place and you end in the same place. Okay, that's the perfect tourist trip. Okay, and so you cross all of the bridges as well. Okay, so you can have a go at that for a moment, but also just chuck it. Let's just chuck in another problem here. There's the classic bored student thing that they draw in their books, or at least used to. There's the envelope problem. Okay, there's this kind of envelope thing like this. So we've got vertices here, 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 and here. You could potentially have a vertex in the middle, but you could likewise put this middle line around here. You could wipe it out and just rearrange that graph. So normally there's the 5 vertices there, and the idea is that you need to, without taking your pen off the page, draw this picture and with one single line, okay, without repeating any lines, and you can end up at a different place from where you start. In fact, I think it's not possible to end up at the same place as where you start. Okay, so just 2 minutes to play around with those and to come up with some ideas on that one. Go. Okay, and if you're still with me, then, or if you're back again, then let's have a look at these problems as well. So the first one, let's have a look at this one here. So the Königsberg Bridge problem can be changed into this network here. So we've got one bridge, we've got essentially 4 land masses, which are your vertices. Okay, and we have 2 bridges, that's these 2 here, going between one side and the island. We have another 2 going here, so it's strongly connected? No, strongly connected anyway because there's no directionality here. There's the bridge going across here, and then there's the bridge there and the bridge there. So that's the network which we have. That's the graph that we could draw in this case. Okay, so there's our two versions. Now, if we go with the first one, you should have been able to find out that if you start in one of the bottom corners, so you can go, I've really doubled that. So we go 1, 2, 3, 4, 5, 6, 7, 8, and there we go, we've completed it. You can probably do it in different ways. 1, 2, 3, 4, 5, 6, 7, 8. It's okay to go through vertices more than once, of course, but we've now drawn it. And in fact, as long as you start in one of the corners, you will always make the picture. If you start here, you won't. You'll get stuck somewhere. In fact, you'll get stuck. Say, for example, here we go. I'm stuck in this position. I'm stuck there now. Okay, so I'm stuck at one of the even node because I'm essentially going out and coming in, and I'm stuck because I don't have a 5th option to leave. So if I want to leave again, I need an odd number of pathways coming out from my vertex. In other words, the degree of the vertex needs to be odd. Okay, so in this case, you can see I can leave, I can come back, I can leave, that's good. But then I'll definitely be going into this at some stage for the first time. I can leave and then I can come back. So I can end there. So I can start here and I can end here. But if I had another vertex of order 3, then I'd have another problem because I would have gone through it once, but I can't get back into it because I'm stuck here now. Okay, so you can't have, in order for you to complete these problems, you can't have more than 2 vertices of degree 3. If you have 2 vertices, you can start in one of them and end in one of them. But if you have more than 2 vertices of degree 3, then you cannot complete the problem. So that's what's called an Eulerian trail. Okay, I'll talk about it more in a second. And there's also things called Eulerian circuits, and the circuit basically means we start and finish at the same place. Now, looking at the Königsberg bridge problem, we can see we have a vertex of 3, a vertex of 3, a vertex of 3, and a vertex of degree 5. So we have a problem here because we have more than 2 vertices of degree 3. So we could leave this one, come back in, leave again, enter this new vertex of degree 3, leave, and then come back in to that vertex of degree 3, and now we're stuck. Okay, right, so you can see that this is not possible. Okay, there is no Eulerian trail in this case. Okay, now why this is called the Chinese postman problem is because the postman wants to walk down every road once and only once, and doesn't want to repeat roads. And hopefully the postman wants to start back at the beginning place as well. They don't want to finish, at the place where they started. Okay, so it's about traveling every single edge, and it's about not repeating edges, the postman problem. Now, if we wanted to, let's just go back a little here. If we wanted to make this circuit here, or this picture here, so that you could start and finish in any place, what we'd need to do is add another edge. We'd need to add an edge between these two to make both of those degree 4. So we need to add this edge in here, potentially. Okay, we could, I think that's actually the only option there, really. You could potentially go a long route. You can go through there and there and there. That would also increase all of the edges to an even degree, but it's just overcomplicating things. Okay, so now let's try this one. Let's try and let's start anywhere. So let's start at the top this time. 1, 2, 3, 4, 5, 6, 7, 8, 9. It doesn't matter where I start now. I start and finish at the same place because they all have an even degree on their vertices. Okay, right. And that's essentially what we need to do for the Chinese postman problem. We need to say, well, look, we've got this network which we need to walk, but in order for us to start and finish in the same place, if that's what we seek to do, then we're going to need to make 2 of our odd vertices, or essentially all of our odd degree vertices, even. And we'll need to do that by adding a path of the least length. In this case, potentially this one. But if this is a weighted graph, it might actually be that I'm going to need to add this here and this here. So duplicate those lengths there. Maybe that's the shortest way of getting from here to here. Okay. Right, so recap then. Eulerian. Recap. Basically, we've got some graphs, and we're trying to travel every single edge and not repeat them. If you can travel every single edge and not repeat them, you have either an Eulerian trail, so after the mathematician Leonhard Euler, so Eulerian trail or an Eulerian circuit. Now a circuit is different to a cycle because a cycle was something like this. It's cycle is just a closed loop between some of the vertices in your graph, but a circuit takes into account needs to go via all of the vertices. And likewise, a trail is different to a walk because a walk can go in any direction you want. It's also different to a tree because a trail needs to take into account all of the vertices. This is all about the vertices. So, as I was just saying, this is all about the edges, not the vertices. So, trails and circuits are about the edges, not the vertices there, as I was misspeaking. It's about a trail has to cover all of the edges as the postman would and return either to the start, which would make it into a circuit, or return to another point in the network. So start and finish at different places, but have to cover all of the edges. And also you'll notice here that I've done a nice job in misspelling this, not trial, trail. Okay. So these are trails. Now, I was also mentioning briefly that later on in 2 exercises time, there's they deal with cycles and paths, and the difference there when they talk about Hamiltonian cycles and paths is that is all about the vertices. In fact, so that's the traveling salesman problem, and it's important that you know the difference between a trail, a cycle, a path, and a circuit. Trail and circuit together, okay? So trail and circuit are all about completing the edges, okay, whereas a path and a cycle is about completing the vertices, but not necessarily all of the edges. So that's the salesman problem, where the salesman needs to visit all of the cities, but doesn't need to necessarily drive all of the roads. Okay, so hopefully that's cleared up. And let's move on to one of the examples. Now, by the way, the Chinese postman problem does require us to return to the starting vertex. So although an Eulerian trail means to say that we're allowed to finish in a different place, the Chinese postman problem wants us to turn our circuit into an Eulerian circuit, okay? So it wants us to start and finish at the same place, in which case all of the vertices need to have an even degree. Okay, so if we have a look at this one then, let's just zoom in. Let's just take the first one here. And let's take this. So 15G, we're just having a look at the first problem. It says, solve the Chinese postman problem for the graphs below, starting at vertex A. State the edges that are repeated and the weight of the route which is taken. So first thing we need to do is think about the degree of each of the vertices. So it's degree 2, degree 4, degree 3, degree 2, degree 3, degree 4, degree 4, and degree, yeah, there we go, that's done. Okay, so we can see that if we wanted to, we could start and finish at E and C respectively. So, you know, that we could do that, you know, any way you want, to be honest. Here we go. Okay, so it always works. It's not particularly clever, but you can, as long as you start at E, you can end at C. No problem. So our issue here is then if we don't want to, if we want to start and finish at the same place, and here they're suggesting that we start and finish at A, then just imagine for the moment that you started at E, you'd end at C. So you'd need to then repeat from C to E. So somehow we need to repeat a journey here. We need to put in an extra journey from C to E. So we sort of need an extra line, but we're going to do that by putting in the shortest route. Now, the shortest route could be quite difficult to find, in fact. It might actually be that these are the shortest routes and that you have one on each of those as the weight. So you do need to look carefully to find the shortest route here. Now, but often it's either going to be this one or this one here. Now you can see The first one I drew through F is 12, has a weight of 12, and through D it has a weight of 16. So through F would seem to be the best option there. Just looking around, yeah, it's clearly the best option. Okay, so C to F needs to be repeated, and so does F to E. Those are two additional connections which we need to put in. I guess if you wanted to, you could put it in as a single line there, but we should show the examiner what we're doing. And that's also going to be of length 7. Let's just put 7 like that. And then this is also going to be of length 5 as well. Okay, so now we've made this circuit Eulerian. That's what we've done. Okay, now it's possible to solve the Chinese postman problem. So it says state the edges which are repeated. So you can say CF has been repeated and EF has been repeated. And the weight of the route taken. Now, it doesn't ask us for the route taken in this case, so we're pretty much done. We just now need to add up all of the edges. So we're going to need to add together 8 and 9 and 7 and 10 and 6 and 11 and 12 and 6 and 10 and 7 and 5 and 7 and 5 again. And potentially they're going to ask you for a viable route as well, which is kind of annoying for an examiner to mark, to be honest, because there are so many different options. So the examiner has to go around and check that you've done it right. So, you could say, look, I start at A, I go to B, and from B I go to C, and so on, okay? Just write it down as you go. Let's do an example of that. You go A to B to C to D to E to G to F to E to F to C to F to B to G to A. It always works. As long as you start at A in that case. Okay, so that is done. That's the Chinese postman problem solved. Now, I'm going to do the next exercise as well, because the next exercise is only slightly different. And instead of having 2 vertices which are odd, they now deal with 4 vertices which are odd. So you're going to need to make 2 sets of connections there. Now, in your exams, you're not expected to be able to do this with any more than 2 pairs of odd degree vertices. So that's as complicated as you can go. So let's have a look at one of those questions too. And I mean, obviously, have a go at the examples here as well, because they can come up with some nice additional constraints. Say for example, if it says, if he in this case, for example, 2b, it says if he walks down any street for a second time, it takes 1/3 of the time, as he does not need to deliver the letters. That's fine, but in the diagram which we've just created, if that was the case, then it would still be that 7 and 5 would be repeated. It's just that they would take 1/3 of the time. So instead of adding 7 and 5, we'd add 1/3 of 7 plus 5. Okay, so that would still be the best section to repeat. Okay, so let's look at the next exercise. It's the bottom of the page here, and let's try exercise 15H. Now, I remember from doing this in class that the wording of this was a little strange, I thought. I was trying to get my head around this wording here, and I thought it was a little ambiguously worded. So it says here, for each of the following graphs, list the 3 pairings that connect 2 vertices of odd degree. So where are the odd degree ones? We've got H, B, F, and D. So list the 3 pairings that connect 2 vertices of odd degree. So do they mean the 3 paths which connect H to B and each of those pairings? So we've got this path, and this path. And perhaps that's what they mean. So H to F, this path, and this path. But what about when it comes to the pairings between H and D? Do we have, those are 2 odd degree vertices that could be connected. Could be that this and this is our best route to make pairings of the odd degree vertices. So where are the three pathways there? 1, 2, 3. Because potentially there's another one. Potentially you could go this, this, this. Maybe that's quicker. So I don't quite understand the question there, but essentially what we need to do, and I think obviously the question needs to be extremely clear, and it says, and find the minimum weight of the walk between each of the vertices. Now that's fairly straightforward to do. So I mean, I would say, look, for H, what's H could be connected to H to B, H to F, and H to D, and then we've got B to F and B to D. We've already considered B to H, and then we've got D to F, and those are all of the journeys which we need to consider. Those are all of the connections which we can consider. Okay, so D has already been connected to H and B previously. Now we can consider that there are many ways to connect H to B. We could consider that there is, you could do H A B, you could do H B itself, you could do H I B. I mean, potentially there's a really short route all the way around the outside if they all had one on them. Okay, now obviously you want to be as clear as possible to the examiner. Now I'd probably say H to B, the shortest route is just 4. So shortest route is just H to B. Now H to F, and let's say route, and you can say that this is the shortest length here. And so the route in this case is actually just A to B. And for H to F, you can see that the shortest route is actually H to F. So that's 6. So the route is H to F. Now let's look at H to D. So we have the option of 6 across there. We have the option of 9 here. We have 12 there. Do we have anything else that we can consider? No, I think 6 is the quickest there. So H to D is also just H to D. Okay, H to D, and then B to F. So B to F is 7 through that route, and again, I think that's the quickest. Through I again. Oh, sorry, when I wrote H to D, it was through I, wasn't it? So then that's B to F is also 7. So that's B, I, F. B to D. So ultimately, I need to choose 2 of these, right? So B to D is, again, it's just the 5. So that's 5, and that's B to D, I think. And then D to F. D to F looks like it's quicker to go through I, so you've got a length of 5 there. Now there's lots of options that you can consider. You could consider this, this, this. So we've got D, I, F here, which is also 5. Just let me pause because I need to just stop the washing machine. Okay, it was just beeping righteously in the background. Right, okay, so there's our particular route. So we need to make a choice of routes here of the lowest length, which is going to make our vertices of degree 3 or our odd degree vertices even. And then the problem is easy to solve. And then, the solutions to the Chinese postman problem can essentially start wherever you want. We could start at A if we wish to, but it doesn't matter where you start. Okay, so let's have a look at these then. So it looks to me that HB would be good to use, so this length here. But it could be that the other option then of connecting F and D, which is what we want to do, could be that that's 15. And so there's a better other option here. It might be that this and this is better if this is then 15, for example. So, it looks like 4 might be the best option, but you have to decide yourself which of the combinations gives you the lowest combination, in fact, of pairs. So HB and BD, so DF looks like the best option in this case. So DF being 5. So those are the best ones to repeat, I think. Okay, so that's going to give us a total of 9, and that's the best possible situation, isn't it? Because we've got 4 and 5 to add together. So the best possible situation is to repeat those lengths there. So we can repeat this one, put another 4 in here. Really need a bigger diagram, and we can repeat this edge here and this edge here. So now that's going to give us the solution to the Chinese postman problem. Okay, right. So ultimately, we just need to add all of our lengths together now, and of course, make sure that we're adding in the 4 and the 5. In other words, the additional 9 here. And then you can list your route if you want to as well, but it's going to take ages to go through that. So, of course, you can come up with any route you like from there. You can say, A, B, C, D, B again. We can do all of this, no problem. Okay, and that completes it. And we can do that in any way we want. Okay, right. Well, that is done. Obviously, just be clear about how you're laying things out and the choice of route which you're going for here. I just had another thought. Did it mean here, because I thought this was slightly ambiguous in the wording, did it mean potentially think about your pairings that connect two vertices of odd degree? So it could be HB and DF. Maybe this was what it meant. And could be HF and BD, and consider the other pairing. What's the other pairing? HD and BF. Okay, I think that's the 3. Perhaps that's what they meant. Okay, consider each of those as options. Okay, and of course you could take that further as well. HB and DF, if we wanted to consider those pairings, that's 9 as a total. HF and BD gives us a total of 11, and HD and BF gives us a total of 13. Yeah, perhaps that's what they meant. Okay, but this was a nice little table to come up with over to the side there as well. Okay then, guys. Well, thanks for listening in. I think this is pretty nice stuff. Get some practice. Again, should only take you a lesson to get this sorted, I think.